Hello again. This is video lecture 32.1, and we're starting chapter 32, which has perhaps an enigmatic title to you, Maxwell's Equations. What are we going to do here? Well, it turns out that the behavior of electric and magnetic fields together, and they do go together. The chapter on electromagnetic induction taught us they're connected. That really almost everything you need to know to understand the behavior of electric and magnetic fields is described mathematically in four equations. Four equations. If we give them their historical names, they are Gauss's law for electric fields, Ampere's law for calculating magnetic fields due to currents, Faraday's law for electromagnetic induction, and then there's one more. And this first section of chapter 32 is about this fourth and final, electromagnetic law. We'll call it, for lack of a better name, Gauss's law for magnetic fields. This is section 1 of chapter 32. Let me just remind you of what Gauss's law for electric fields says. So G, law for E fields. Okay? The electric flux, phi electric, through a closed mathematical surface, S, closed surface, like the surface of a blown-up balloon that's been tied off, filled with air and tied off, nice and stretched. Then the surface of that balloon is a closed mathematical surface with a well-defined interior volume and then everything that's exterior. And when you calculate the total electric flux through a closed mathematical surface, the answer you get for that calculation will be equal to the total electric charge that is inside the surface divided by that old friend, the constant epsilon zero. That's Gauss's law for electric fields. What is the corresponding formula for magnetic fields? This result is based on experiment, and it's based on the following empirical result exemplified by looking at a bar magnet. A bar magnet, look at the picture on the left, has a north pole and a south pole, and you have magnetic field lines created by a permanent bar magnet, and the magnetic field lines come out from the north pole end, circulate around, and then come into the south pole end. And the picture on the left is a bar magnet with some iron filings scattered around it and then illuminated so that you can see it. And you can kind of see the structure of the magnetic field lines by looking at, let me use a better color than that, by looking at how those little iron filings are lining up, like that. Okay? All right, that's called a magnetic, it's a bar magnet, it's called a magnetic dipole because one end, let's say that end, is a north pole and the other end is a south pole. And then here on the right, you have a schematic representation of a bar magnet with a north pole and a south pole. Now, what about the concept of a magnetic monopole? What about a bar magnet that's just, say, a north pole, just north, or just south? That would be called a magnetic monopole, as opposed to a north and a south, which is a magnetic dipole. Couldn't there be such a thing? In fact, wouldn't all you have to do is take that bar magnet there and snap it into, say, two pieces? Then wouldn't the top piece be a north pole and the bottom piece be a south pole? Seems like a reasonable thing to assume, but it turns out that isn't what happens. The bar magnet will automatically rearrange itself no matter how many pieces you break it up into. And here we draw 3 pieces. And the pieces will always then rearrange themselves so that they have both a north and a south pole. So I've gone from one big magnetic dipole to 3 small magnetic dipoles. We have never found any kind of evidence for a bar magnet or anything equivalent to it that is, say, just a north pole. We don't find it in nature. It doesn't mean there's no law of physics that says you couldn't have that in principle. But experiments show, apparently, that we don't. And there have been a lot of searches. So, we take as an empirical fact that there are no magnetic monopoles. At least we don't know of any at the current time to exist. If there are any, they're very elusive. And so that what you find in terms of the simplest magnetic structure out there is a magnetic dipole. You could have something called a magnetic quadrupole or an octopole. You can have more complicated things, but the simplest thing is a magnetic dipole. And, like with a bar magnet, the magnetic field lines always form closed loops. There's no beginning or end to them. So now let me show you another schematic of a bar magnet. Let me zoom in here. With a north and south pole and a schematic drawing of some of the magnetic field lines that go with that bar magnet. And no matter which magnetic field line you care to follow, like this one, you will discover, even though it might be a complicated shape, that it's just a loop that closes on itself. There's no beginning or end. It doesn't start on something and terminate on something. It's just a closed loop. Here's another one. Now, they don't show here, but you have to imagine it goes out like that. Comes back in, like so. Okay? And that's the case with every one of the lines you see. They're actually all closed loops. Okay? That's the upshot of having always a north and a south pole together. Okay, so what does that mean? What are the consequences of that when it comes down to calculating the magnetic flux through a closed surface? Okay, here we go. If the magnetic field lines always form closed loops with no beginning or end, then the consequence of that is the magnetic flux through any closed, double emphasis, closed surface must equal 0. And then, now let me go back to that drawing over here. I'll zoom it out again. They're trying to represent that here in the diagram. It's not that great, but let me explain. You see this red kind of oval shape that they label surface 1. What they really mean by drawing that red oval shape is that you have to imagine a closed surface, like a blown up balloon. And they're just drawing it to look like it's an oval, but it really represents a closed mathematical surface, like a blown up balloon of this shape. And then what they're pointing out is that every magnetic field line that pierces that surface, surface 1 they call it, going inward, will somewhere later pierce it going outward. Every single magnetic field line will do that. If it pierces surface 1 going in, it will also pierce it going out. But magnetic flux is the net. It's a quantitative measure of the net piercing of a surface by a magnetic field. So if every magnetic field line pierces going in and also then somewhere else going out, guess what you get for the total magnetic flux, total, through the whole surface? You get 0. So when you calculate the magnetic flux through a closed mathematical surface, and that's what the little circle there means, on the surface integral symbol, you will always get 0. Now that's called Gauss's law for magnetism, because it tells you what you get when you calculate magnetic flux through a closed surface. Just like Gauss's law for electrostatics tells you what you'll get when you calculate electric flux through a closed surface. And in the magnetic case, it's very simple. You will always get a total magnetic flux through a closed surface equal to 0. Now let me try to be very clear about what this is not talking about. Gauss's law for magnetism is not, emphasize not, talking about the magnetic flux through a loop, the surface of a loop. So for example, let's draw a circular loop seen at an angle. Okay? That's the perimeter of a circular loop. We can imagine a surface bounded by that loop, S, on the inside of the loop. That is not a closed surface. Okay? That is not like the surface of a blown-up balloon. It's more like the surface of, say, a soap film that would be formed within the perimeter of the loop. It's flat surface. It's not closed with an interior volume. And then I can put it near a bar magnet, and there can be magnetic field lines that cut through it, pierce through it, like that. There is a magnetic flux through that surface, okay? Because there's piercing going through. What we're talking about with Gauss's law for magnetism is a closed mathematical surface, like the surface of a blown-up balloon. And there you will discover that the total magnetic flux is always zero. Okay, so that's the point of this video. I'm going to leave you with a class engagement exercise, but I'm going to help you set it up a little bit, okay? Because it's a little bit abstract, Gauss's law for magnetic fields. Here's what we have. The figure here shows 4 closed surfaces. Again, you can always imagine a blown-up balloon. It's just that the shapes of these balloons are, a bit different, okay? We have 4 closed surfaces. Each of them has a flat top face and a flat bottom face, and the sides are curved, okay? So these perspective views clearly show the flat top face on each. They don't show the flat bottom face, but if I try to sketch it, for example, for the first one, it would be something like that. And for the second one, it would be something like that. Maybe a little bit bigger, but roughly like that. For the third one, the flat bottom face is roughly like that. And for the fourth one, the flat bottom face is roughly like that. And then those sides, you can see, are curved in various ways. Okay, then we have a table here, as you can see, for the four surfaces, A, B, C, and D. And in this table, we are given the area A of the top face and the bottom face, and the magnitude of the magnetic field B, which is uniform and perpendicular through the face. The units of area and magnetic field are arbitrary but consistent. So let's look at the table. Okay? For example, for surface little a, the area of the top face is 2 units. That would be this area right there. And the magnetic field up there is perpendicular and uniform and has a magnitude of 6 units. You can think Tesla if you want, outward like that. Whereas the area of the bottom face is larger, 4 units, and has a magnetic field of 3 units inward. Notice how I'm drawing it. And that describes surface A. And then you have similar information for surface B, surface C, and surface D. Here comes the question, or the task. We are to rank these surfaces according to the magnitude of the magnetic flux through the curved side, greatest first, for each one. You got to figure out how big is the magnetic flux, not through the top, at least that's not going to be the answer, not through the bottom, but through the curved side. So let me help you set it up a little bit here to get you started, but then you're going to finish it and putting your answers on Blackboard. Well, it's practice with Gauss's law for magnetic fields. Gauss's law for magnetic fields could be written this way. The net magnetic flux through a closed mathematical surface must always equal 0, no matter how complicated that surface is, as long as it's closed. In our 4 cases here, we have somewhat messy or complicated looking surfaces, but they have similar characteristics. They have a flat top face, a flat bottom face, and a curved side. So it's quite natural to break up that expression for the net magnetic flux into an expression for the magnetic flux through the top face, plus an expression for the magnetic flux through the bottom face, plus an expression for the magnetic flux through the curved side. Right? You can calculate the flux through each of those pieces separately and add them up as scalars, and the grand total must be 0. Now, with that table, you should see now that they have given you enough information to figure out phi b top, and enough information to figure out phi b bottom. So you should be able to use this result to solve for phi b through the curved side. And when you do that, you got to do that for all 4 surfaces, and then you can see the ranking by looking at those answers. Okay? All right, so that's the video lecture. And then I'll be having a class video where we'll be applying this idea. And that's all for this video.